This video is going to explain to you a new way of graphing. We're going to be graphing equations called parametric equations. This is in chapter 10 of your textbook, 10.5 in fact. And up until now, the equations that we've been graphing has been a single equation in two variables. The graph has been something like y equals x squared minus 2x plus 1, for example. That's a single equation. It has two variables, x and y. And if I were to ask you to graph x squared minus 2x plus 1, you would convert it into vertex form. Y equals x minus 1 squared, which, as you remember from the fall, is just a parabola that's been shifted to the right 1. It has a vertex at 1, 0, and it just follows the normal parabola shape. When we work with parametric equations, the advantage of parametric equations is that they're very useful in showing movement of a particle along a curve. If I wanted to explain how a particle moves along this curve, you really don't know whether the particle moves from left to right, right to left, where it is started, or how fast it's going. So parametric equations introduces a new variable into the whole scheme of things, and it's a variable that represents time. So parametric equations are actually defined as x is some function of t, y as another function of t, and together the two equations that define x and y, both being functions of t, together these are called parametric equations. The t variable usually represents time, and the x and y represent the x and y coordinates at a certain time t. T can be in seconds or minutes or whatever we define it to be. So I'll give you an example of this parabola that I showed you earlier, how it could be represented. One of the many ways it could be represented as a parametric set of equations. Let's let x be equal to t plus 1. That's our function of t for the x variable. And let's let y equal t squared. So together these two equations make up the parametric equations. And if we were to graph this set of parametric equations, we are going to use something called a t-chart, or we're going to represent x, y, and t as the three different variables instead of just x and y. So I'm going to ask you, or we're going to together graph this for all values of t. We usually let t start at 0 because time usually starts at 0, but it doesn't have to be that way. Sometimes t can go negative. We'll let t go between 0 and 0.4. Okay. So what we need to do if we wanted to graph these parametric equations for this set of t values, we set up a t-chart. It's nothing more than a table of values, and I'll let t increase from 0 to 4 by 1 second intervals, and it doesn't have to be 1 second intervals. You can increase by a half a second or 2 seconds or whatever you want, or whatever you're asked to do. So here are the values of t within the range that I've asked you to graph. And now what we do is we just substitute t into the x and y, and we come up with x and y values. So when t equals 0, you let t equals 0 in the x equation. 0 plus 1 is 1. And you let t equals 0 here, y equals t squared, so y equals 0 squared, which is 0. When t equals 1, t plus 1 is equal to 2. T squared is equal to 1. When t equals 2, 2 plus 1 is 3, and t squared is 4. When t equals 3, 3 plus 1 is 4, and t squared is 16, and I'm sorry, with 9, duh. And then when t equals 4, 4 plus 1 is 5, and 4 squared is 16. So these are the xy coordinates that we're going to be graphing parametrically. So the graph of a parametric equation looks pretty much like the graph of just any old equation that you've done before. But what we have to represent is the t values along the way. So at time equals 0, like I said, this represents particle movement. So when t equals 0, the x value is 1 and the y value is 0. So this particle actually starts right here at the coordinate 1, 0. And we represent this by t equals 0. And this is x and this is y, just like it always has been. So at t equals 0, here's the particle. At t equals 1, the particle moves to 2, 1. So over 2, up 1. At t equals 2, the particle moves to 3, 4. At t equals 3, it goes to 4, 9, which is kind of off my chart, and 5, 16 would certainly be off my chart. So here is the parametric view of this particle movement. It starts at t equals 0, and along the way, this is where the particle moves to. At t equals 1, 1 second, the particle's here. T equals 2, 2 seconds, it's here. And then on we go up to 3 and 4, and it gets out of range of this graph. And you can kind of see that this is half of the parabola that I graphed up here. If we had let t go from, say, -4 to 4 or -2 to 2, we would have set up our t values from -2 to 2 or whatever those values would be, and then you would have seen the x and y values being going in this direction over here. But I didn't. I let t equals 0 to start with. So here's kind of a half a parabola that we graphed before. Now the important thing about parametric equations is because it's representing particle movement, you want to put arrows along the way to show that the particle is moving up to the right and not down to the left. So parametric equations aren't all that complicated, and we'll just go through another example of them, and then I'll show you another thing that we do with parametric equations. So this is just example number 2. In example number 2, I'm going to ask you to graph the curve defined. You know what, we can say defined parametrically. By the equations x is equal to t squared and y is equal to t minus 1. And you can see this is somewhat similar to what we had just graphed before. Now t is the parameter. If you hadn't gotten that yet, t is called the parameter. And usually, not always, but usually it represents time. Okay, so now we're going to let t go from, let's say t is going to go between -2 and +2 inclusively. So we'll get a better shaped parabola in this one. They're not always parabolas, but in this particular case you'll see that it will be. Okay, so we'll set up our t chart and we'll let t go from -2 to +2. And we set up our x and y variables. And when t is equal to -2, -2 squared is 4. And actually it's probably quicker just to go down the x values here by just squaring each one of these t values. So we get 4, 0, 1, 4. And then the y values, negative 2 minus 1 is negative 3, negative 2, negative 1, 0, and 1. So now we have a set of x, y values that we're going to be graphing parametrically. So we're going to set up our xy table. It looks like our x max is going to be out to 4 and our x min is 0, so we can actually, we don't really need any negative x values here. And our y values go from positive 1 down to negative 3. So positive 1 down to negative 3. All right, so our first set of coordinates are 4, negative 3. So go over 2, 3, 4, and down to negative 3. So this is where the particle starts. The particle starts this time at t is equal to negative 2 down here. And then 1, negative 2. 0, negative 1. 1, 0. And 4, 1. So this parabola is a sideways parabola. It's not a function. That's one good thing about parametric equations, is that you can graph all sorts of curves, and they don't necessarily have to be functions. A lot of them will fail this vertical line test. So here's t equals negative 1, t equals 0, t equals 1, and out here t equals 2. So we can follow this movement of the particle along this path from t equals negative 2, and you have to put the arrows on your graph because that shows the direction of movement. So you might want to write that down in your notes. Must put arrows on graph to show direction of movement, and indicate t values along the path. So we want to know exactly where this particle is at any point in time. All right, the next thing I'm going to show you about parametric equations, because it really doesn't get much more complicated than that, is I'm going to show you how to do something called eliminate the parameter. All right, eliminating the parameter. If you remember, I said the parameter usually is t. So eliminating the parameter means just getting rid of the t value. And when we get rid of the t value, what we get, what the result is a regular equation, a single equation in x and y. All right, this single equation in x and y is called the rectangular equation. That's an important vocabulary word for you, the rectangular equation. All right, so you have, what we're going to do is we're going to go from a set of parametric equations to a single rectangular equation. And you just go through a couple of steps. It's pretty simple. The first step is to solve for t in either x or y parametric equation. Step 1. And then step 2 is just to substitute in for t into the other parametric equation. So I think I'll go through both of these examples that I gave you to graph, and we're going to eliminate the parameter in each of these two examples. So example 1, I said x equals t plus 1 and y is equal to t squared. That was our example that we used before. Yes. And my job is to eliminate the parameter. So the easiest thing for us to do is to solve for t. You can solve for t in either of these equations, but I usually like to take the lowest power of t, so I'm going to take this linear equation. So solving for t in this x equation, we're going to get x minus 1 is equal to t. All right, just subtract 1 from each side of the equation. That's step 1. Solve for t in either the x or the y. I chose the x. It was easier. And then in step 2, we're going to substitute x minus 1 in for this t value right here. So step 2 says y is equal to t squared, but it's not t squared, it's x minus 1 quantity squared. And that's it. Now what you have is the rectangular equation. One equation, two variables. I'm out of room down here. And so then I'll take the second example that I gave you up here to graph this sideways parabola, and we'll just eliminate the parameter here, which is pretty much the same process, except I'm going to solve for t in the y equation. So x equals t squared and y equals t minus 1. Oh, my poor camera. X equals t squared and y equals t minus 1. And my job is to eliminate the parameter. And so step 1, I'm going to choose this y equation because it's the linear equation. So y plus 1 is equal to t if you add 1 to both sides of the equation. In step 2, I'm going to substitute y plus 1 into this x equation. So x is equal to y plus 1 quantity squared, step 2, and that's the rectangular equation. And this is a parabola, but instead of y equals some function of x being squared, this x is equal to some function of y being squared, and that's what produces this C-shaped parabola. So that's it for today. Just introduction to what parametric equations are, what they're used for. They're used mainly to show the path of a particle moving along some curve through some set of t or time values. And then if you want to change a parametric equation into just a regular rectangular equation that we're used to graphing, you go through the process called eliminate the parameter. So we'll get some practice on that in class.